a realm where reality itself feels profoundly counterintuitive. We're talking about the quantum world, a place where particles can seemingly exist in multiple locations at once, or a single quantum bit, a qubit, can simultaneously be both 0 and 1.
Right, superposition.
Yeah.
It's fundamental.
Exactly.
Yeah.
This superposition, it's at the heart of quantum mechanics, but it stands in, well, stark contrast to our everyday experience.
Yeah, absolutely.
You certainly don't see your coffee cup sitting in a superposition of states, right?
Well, unless something's gone very wrong with breakfast.
Exactly. So this vast conceptual chasm between the microscopic quantum realm and our familiar macroscopic world, that's precisely where our deep dive begins today.
And bridging that very chasm is the pivotal concept we're exploring. Decoherence, our main source for this, decoherence, quantum entanglement, and classical emergence, really serves as our guide here. It basically reveals that the smooth transition, from quantum weirdness to classical certainty isn't some arbitrary rule we just added on. It's an emergent phenomenon, a natural, almost unavoidable outcome of how quantum systems interact with their surroundings.
So our mission today, then, is to unravel this fundamental process. We'll unpack what decoherence actually is, how it works, why it's so utterly unavoidable.
Unavoidable is the key word there.
Yeah, and its profound implications, not just for understanding reality itself, but maybe more pressingly, for the future of quantum technologies.
Definitely.
Okay, let's really get into this.
Yeah.
So at the very core of those mind-bending quantum phenomena we mentioned, like superposition, entanglement, lies something called quantum coherence.
Right, coherence.
Think of it as the bedrock, the thing that allows a qubit to hold both the 0 and 1 states at the same time.
Exactly.
And the classic double-slit experiment is the perfect illustration, isn't it?
Oh, absolutely, the classic.
When an electron goes through two slits, it doesn't just pick one path. Its wave seems to propagate through both.
Both slits.
And that interference pattern you see on the screen, that's the undeniable signature of quantum coherence. Direct proof the particle's state contains information about both paths simultaneously. It's really remarkable stuff.
It truly is. And yet, as you pointed out, in our macroscopic world, that kind of interference is conspicuously absent. We just don't see it.
Never.
And decoherence is the study of why this suppression happens. It occurs when a quantum system, like that electron, isn't perfectly isolated. It inevitably interacts with its environment.
Okay, so interaction is key.
Absolutely. In our double-slit example, just imagine tiny stray photons or even air molecules scattering off the electron.
Okay.
Each tiny interaction acts like a minuscule unintended measurement. It effectively marks which slit the electron passed through.
It leaves a trace.
Exactly. Once that which path record exists out there in the environment, the delicate phase relationship, that coherence, that was once neatly contained within the electron alone, it becomes delocalized. Spread out, yes. It becomes part of the bigger system, the electron and whatever particle interacted with it. So from the perspective of just the electron, its coherence seems lost.
Right.
The interference pattern vanishes, and it looks exactly like a classical particle, just picked one slit and went through it.
So if I'm understanding this right, the central idea, the thesis, is that decoherence isn't some new extra rule added onto quantum mechanics.
Not at all.
It's a direct, and you said inevitable, consequence of a quantum system unintentionally entangling with the vast, unobserved bits and pieces of its environment.
Precisely. It's just standard quantum mechanics, but applied realistically to open systems, systems that are never perfectly sealed off.
That's a profound realization when you think about it. It's not extra, it's inherent.
It really is. And an intuitive way to kind of grasp it is as information leakage. But crucially, it's not like classical information loss. We're talking about the unique quantum phase information. Imagine a tiny drop of red ink in a vast ocean.
Right.
Initially, the ink's redness is localized, concentrated. As it disperses, the ink molecules aren't destroyed, but their redness becomes so incredibly diffuse, spread out across trillions of water molecules.
Yeah, good luck finding it again.
Exactly. From a local perspective, it's practically irretrievable. Similarly, quantum phase information isn't destroyed. It just leaks out into this complex web of system-environment entanglement. It becomes locally inaccessible to us.
That's a great analogy. So it's not truly lost, just diluted beyond any practical retrieval. Does that mean, like, in theory, if we could perfectly track every single molecule of that ocean, we could retrieve the redness?
In principle, yes. If you had godlike ability to track all the environmental degrees of freedom, the total information is conserved. and this is crucial. Decoherence transforms local quantum information into inaccessible, non-local information. That makes it very different from mere classical noise, which often involves energy loss or randomization that is truly unrecoverable.
Got it.
And it's universal because, fundamentally, no quantum system is ever completely isolated. I mean, the environment is literally everything else. The cosmic microwave background, thermal vibrations, even tiny gravitational fluctuations.
Wow, everything.
Everything. For macroscopic objects, like even a tiny speck of dust, decoherence happens unbelievably fast. We're talking fractions of a second, like 10 to the minus 27 seconds. Way too fast for us to ever perceive any quantum weirdness.
Mind-bogglingly fast.
Yeah. So this implies that the default natural state of any subsystem of the universe isn't some perfect, pure quantum state.
Right.
No, it's a mixed state, a statistical ensemble. The mixed state is the norm, and the pure state is the fleeting, idealized exception we might create temporarily in a lab.
All right, so we've established this conceptual chasm and understood decoherence as this inevitable bridge. But how do physicists actually, put numbers to this? How do they model this elusive process precisely?
Right, moving from the concept to the math.
Yeah, this is where it gets really interesting.
Well, to model decoherence rigorously, a simple wavefunction, which describes a perfectly isolated system, just isn't enough, especially when systems aren't isolated or are part of larger entangled pairs.
Makes sense.
That's where the density matrix, usually written as ORO, becomes absolutely indispensable. It's a mathematical powerhouse because it can describe both pure quantum states, where we know everything perfectly, and mixed states, which are statistical mixtures or represent subsystems where our knowledge is incomplete due to entanglement.
Okay, so it handles both certainty and uncertainty.
Exactly.
All right.
And its fundamental properties, things like being Hermitian, having unit trace, being positive, semi-definite, these aren't just math jargon. They ensure the density matrix accurately represents a real physical quantum state.
Right. Keeps it physically meaningful.
Precisely. And a key number it gives us is the purity, calculated as trace. For a pure state, it's exactly 1. For a mixed state, it's less than 1. This gives us a direct quantitative measure of how much coherence has been lost.
So purity here isn't about, cleanliness, but about how crisp or undiluted the quantum information is, how much it's been kind of muddled by interaction.
That's a perfect way to put it. Purity tells you how crisp the quantum information remains. 1 means perfectly crisp, a pure superposition. Less than 1 means it's blurring into a classical-like mixture.
Okay.
And the mathematical origin of decoherence itself comes from an operation called the partial trace over the environment, written TRE.
Partial trace.
Yeah. Here's the really cool part. Even if the total system plus environment evolves perfectly unitarily, meaning it stays in a pure state, conserves all information, the act of performing a partial trace, mathematically ignoring the environment, that forces the subsystem we care about into a mixed state. It's the very act of looking only at the part, not the whole, that makes the subsystem appear to lose its quantum properties.
Wow. So just by mathematically looking away from the environment, the part we see looks classical.
Effectively, yes. And the beautiful, unambiguous signature of decoherence within this math framework is the decay of the off-diagonal elements in that reduced density matrix.
Okay, the off-diagonals. For our listeners, can you quickly remind us what those off-diagonal elements represent again?
Absolutely. So the diagonal elements are like classical probabilities, the chance of finding the system in state 0 at 0 second.
Got it.
But those off-diagonal elements, those are the coherences. They encode all the quantum phase relationships, the very things responsible for interference and superposition.
The quantumness.
The quantumness, exactly. So when they decay and vanish, that quantum weirdness literally disappears from the mathematical description.
Okay, makes sense.
We can use a simple qubit environment interaction model to see this. Imagine a qubit in a superposition, say 0 error euro, as it interacts with its environment.
It gets entangled.
It gets entangled. So if the qubit is in state 0 euro, the environment goes into some state, let's call it E euro. If the qubit is in state 1 euro, the environment goes into a different state, E euro.
Okay.
Now, for a big macroscopic environment, these two environmental states, E or O, rapidly become orthogonal. Their overlap, the inner product, quickly goes to 0.
They become totally distinct.
Totally distinct.
Wow.
And this vanishing overlap directly multiplies the off-diagonal terms in the qubit's density matrix, causing them to decay, often exponentially fast.
Ah, so the environment becoming distinguishable kills the quantum part.
Precisely. What's left is a diagonal matrix, and mathematically that describes a classical statistical mixture. It's as if the qubit just randomly chose to be either 0 or 1 0.
Okay, so just to be absolutely crystal clear for everyone listening, information isn't fundamentally destroyed by decoherence.
Correct. Not destroyed.
It's redistributed. It gets spread out into these non-local, practically impossible to track entanglement correlations between the system and the huge environment.
You got it.
Which makes it a massive practical challenge for building quantum technologies, but it's not some fundamental violation of information conservation.
Exactly. That distinction is critical. It's a practical hurdle, not a theoretical impossibility.
That makes a lot of sense. Okay, so we've dissected the mathematical elegance, how physicists model this, but for you, for me, what does this all mean for us and the world around us? How does this abstract process lead to the definite, seemingly classical reality we experience every single day?
Right, connecting the math back to lived experience. This brings us to a really important concept: environment-induced superselection, or einselection for short.
Einselection, okay.
It directly tackles that long-standing puzzle known as the preferred basis problem. Basically, why do we only ever see macroscopic objects in definite states? Like, why is my pen always here, never in a superposition of being here and, I don't know, over there?
Yeah, the universe seems to have picked its preferred way of showing things to us.
Exactly. And einselection says the environment picks it. The environment doesn't interact uniformly with every possible state of a quantum system. It strongly interacts with certain states, making them much more stable and resistant to decoherence. These are called pointer states.
Pointer states. Like signposts.
Kind of like signposts, yeah. They're the states the environment notices most easily. And for most common interactions in our world, like photons scattering off things, these pointer states turn out to be position states.
Ah, so location is a preferred state?
Very much so. So any superposition of spatially separated states, like the classic Schrodinger's cat being simultaneously alive and dead.
Which involves different locations of atoms.
Precisely. That kind of superposition is immediately discovered by the environment. Stray photons, air molecules, whatever. The environment rapidly destroys the coherence between those distinct position states, leaving only a classical-like statistical mixture. You're left with probabilities of alive or are dead, not both.
So einselection effectively forbids macroscopic superpositions from sticking around.
It forbids them from persisting. Yes, they decohere almost instantly.
Okay, so that explains why we see definite states.
Right.
But how does that lead to an objective reality, where you and I could both look at that pen and agree it's there without messing it up just by looking?
Ah, good question. That's where another really elegant idea comes in. Quantum Darwinism.
Quantum Darwinism.
Mm-hmm.
Okay, intriguing name.
It is. The core insight here is that information about the system's robust pointer states, like the pen's position, isn't just leaked to the environment. It's redundantly copied into many, many independent fragments of the environment.
Redundantly copied.
How? Think of a tennis ball flying through the air. Trillions of photons scatter off it. Each photon carries away a little bit of information about the ball's position.
Right.
Now, many different observers, you, me, someone else, can each capture a tiny fraction of these scattered photons with our eyes. We each get just a small piece of the environmental record. But because the information is so redundantly copied, we all reconstruct the same position for the tennis ball. We agree on its location, and crucially, our individual observations hardly disturb the ball itself.
Because we're just sampling a tiny fraction of the environment's record.
Exactly. This shared, stable, and easily accessible information redundantly encoded in the environment that, according to quantum Darwinism, is classical objective reality. It's why our world appears so stable and agreed upon.
Wow. That's a really compelling picture. So given everything we've discussed about how coherence gets lost and things start to look classical, it's easy to see why people might confuse decoherence with another big quantum idea, wavefunction collapse.
Oh, absolutely. It's a very common point of confusion.
But they are distinct concepts, right? Understanding the difference seems really key here.
It's absolutely crucial. Let's break it down. Decoherence is a physical, dynamical process. It's predictable using the standard Schrödinger equation applied to the system and its environment.
Okay, it's part of the normal evolution.
Right. It explains the appearance of collapse by turning a quantum superposition into a classical-like statistical mixture. Remember, those off-diagonal terms decay. It essentially leaves you with a menu of possibilities and their probabilities.
Right, the or situation, not the A and D.
Exactly. The wave function collapse, on the other hand, is still, in most interpretations, a postulated event. It's non-dynamical, seemingly instantaneous, and it's the thing that selects a single definite outcome from that menu decoherence prepared.
So decoherence sets the stage, collapse picks the winner.
That's a good way to think about it. Decoherence explains why we don't see the weird superpositions macroscopically, and why measurements seem to have definite outcomes ready to be chosen. It doesn't fully solve the problem of outcomes, why only one outcome happens in any single experiment, but it profoundly reshapes the measurement problem for different quantum interpretations, like Copenhagen or many worlds. It makes them much more consistent with observation.
That clarification is really helpful.
Yeah, and the ultimate takeaway here is that classicality, being classical, isn't some intrinsic property an object has just because it's big.
No.
No, it's an emergent and relational property. It depends entirely on the object's ongoing interaction with its environment. You can have a macroscopic object like a superconducting quantum interference device,
Okay.
and if you shield it incredibly well, keep it isolated, it can absolutely exhibit quantum superposition. But then you have a microscopic alpha particle, tiny thing, zipping through a cloud chamber.
Yeah.
It leaves a perfectly definite classical track because it's heavily, constantly entangling with all the gas molecules it hits. Size isn't the main story, interaction is.
So the classical world we see.
It's simply the unselected, chosen by the environment stable, and redundantly recorded part of the one single universal quantum reality underneath it all.
That squee-wide versus alpha particle example really drives that home. Size isn't the defining factor. Okay, so while the concept of decoherence is universal, the precise details of how coherence gets lost must really depend on the specific environmental interactions, right?
Absolutely. The flavor of decoherence changes depending on the environment.
So how do physicists quantify this? How do they build models to predict how fast coherence will decay in different situations?
They use what are often called paradigmatic models, sort of standardized frameworks that capture the essence of different kinds of environmental interactions. One of the most important and widely used is the spin boson model. This is seen as a universal paradigm for understanding thermal decoherence. It describes a simple two-level system, or qubit, the spin part, coupled to an environment model as an infinite bath of quantum harmonic oscillators, the bosons. Think of it like coupling a qubit to a bath of tiny quantum springs vibrating.
Okay, a simplified environment?
Right, but one that captures a lot of essential physics. This model describes two main ways coherence is lost, and it gives us timescales for them, T2 and T1.
T2 and T1, what are they?
T2 is the timescale for pure dephasing. Here, the environment essentially measures the qubit's state without exchanging energy. It just randomizes the phase relationship between the qubit's 0 and 1 IR components. It's like the qubit loses its internal rhythm or timing.
Okay, losing the phase.
Exactly. Then there's T1, which is the timescale for energy relaxation. This involves actual energy exchange. For example, an excited qubit in state 1 IR might decay down to the ground state 0A by giving its energy to the environment, maybe creating a phonon, a vibration in the boson bath.
So T1 is about losing energy, T2 is about losing phase information.
You got it. And generally, T2, the dephasing time, is always less than or equal to twice T1, the energy relaxation time. Usually, phase coherence is lost faster, often much faster, than energy.
Interesting. Okay, so that covers thermal environments.
Right.
What about the electromagnetic environments that are so crucial for, say, quantum computing chips?
Right. For things like superconducting qubits or trapped ions, cavity and circuit quantum electrodynamics, QED models, are absolutely key. And here, specific mechanisms tend to dominate.
Such as?
Well, one is photon shot noise. This is the intrinsic quantum uncertainty in the number of photons in the microwave fields used to control and read out the qubits. Just the unavoidable quantum jitter in the photon number can cause rapid dephasing. It's a form of measurement-induced dephasing.
Just by being there, the control fields add noise.
In a sense, yes. Then you have thermal photons, or blackbody radiation. Even if you cool your quantum computer down to near absolute zero, there's always some residual heat, some stray thermal photons bouncing around. These can cause unwanted transitions, bumping a qubit from 0 to 1Z or vice versa. That contributes to T1 noise.
Even at millikelvin temperatures.
Even then, it's a factor. And finally, there's spontaneous emission, or in-circuit QED, cavity leakage. An excited qubit might spontaneously decay by emitting a photon into its electromagnetic environment, maybe leaking out of the chip. This irrevocably entangles the qubit with the outside world and contributes to both T1 and T2 effects.
So these are the main culprits platforms like superconducting qubits have to fight against.
Absolutely. They are the primary enemies in those systems.
And just to bring it back to something maybe more intuitive, what about just plain old physical interactions, like literally things scattering off a quantum object?
Yeah, that's perhaps the most pervasive mechanism in our everyday experience, and it's brilliantly captured by the Jews and Zay model of environmental scattering.
Okay.
Imagine an object, maybe a tiny dust grain, somehow put into a superposition of being in two slightly different positions, x and x.
Right.
Now, when an environmental particle could be a stray air molecule, could be a background photon scatters off this object, it imparts a random phase kick to the object's wave function.
Okay, random nudge.
A random nudge to its phase. And here's the crucial result from Juice and Zeh. The rate at which decoherence happens due to the scattering is proportional to the square of the spatial separation between the superposed components, XS.
The square of the distance. Why is that significant?
It's hugely significant. It means that even a tiny separation for a macroscopic object leads to an incredibly fast decoherence rate. If you separate the components more, the decoherence speeds up quadratically, not just linearly.
So it gets worse much faster as things get bigger or further apart.
Exactly. This quadratic dependence is why macroscopic objects decohere so unbelievably quickly. Remember that dust grain example? If you could somehow put it in a superposition separated by just, say, its own diameter, environmental scattering would cause it to decohere in something like 10 attoseconds, basically instantaneous.
That speed is just, it's hard to even conceive of.
It is, and this scattering mechanism provides a really direct, compelling explanation for why we live in a world of localized objects, why everything seems to have a single, definite position. The environment, through scattering, enforces it incredibly strongly.
Okay, so these different models, spin boson, cavity QED, environmental scattering, they collectively show us that the environment isn't just random featureless noise, it's structured. Its specific properties dictate the type and rate of decoherence.
Absolutely. The environment has structure.
And I imagine that very structure is what allows scientists to develop mitigation strategies. If it wasn't structured, maybe we couldn't fight it.
Precisely. Understanding the structured nature of the environmental noise rather than just thinking of it as pure random chaos is absolutely key to developing effective mitigation strategies. It allows us, for example, to design quantum systems that are deliberately off resonance with specific environmental noise frequencies, meaning they just don't couple effectively to those particular sources of decoherence. We can engineer immunity to certain known noise types.
Which brings us squarely to the critical practical implications of all this. If we connect everything we've discussed to the bigger picture, this burgeoning field of quantum technologies, especially quantum computing, this is where decoherence shifts from being a fascinating theoretical concept to being, well, the ultimate roadblock, isn't it?
Unequivocally, you could call decoherence the arch nemesis of quantum computing.
The arch nemesis, I like that.
Because the very things that make quantum computation potentially so powerful, those delicate superpositions and complex entanglement, are precisely what decoherence attacks and destroys. It introduces errors, corrupts the quantum information, and ultimately limits what the computer can do.
And those T1 and T2 times we talked about.
They become critical figures of merit. T1, energy relaxation, and T2, dephasing time, quantify how long individual qubits can maintain their quantum coherence before the information degrades. These times impose strict limits on the depth, how many operations you can do in sequence, and the complexity of quantum circuits we can reliably run on current hardware. We often call this hardware NISQ, noisy intermediate scale quantum.
Right, NISQ era.
Yeah.
Because of the noise.
Exactly. Decoherence is the primary reason for the high error rates we currently see in quantum gates. Every operation has a small chance of failure due to noise, and those errors accumulate rapidly.
So the big question then, how do we fight back against this arch nemesis? What strategies are scientists and engineers actually deploying right now to try and preserve that fragile quantum information long enough to do something useful? What stands out to you about these approaches?
Well, there's really a whole toolbox, a kind of taxonomy of mitigation strategies that people use, often in combination. We can broadly categorize them. First, you have the passive mitigation approaches. These are all about isolation and careful engineering.
Okay, building a better box.
Essentially, yes. This includes things like cryogenic cooling, operating qubits at millikelvin temperatures, just thousandths of a degree above absolute zero, colder than deep space, to drastically reduce thermal fluctuations that cause energy loss, T1 noise.
Right. Get rid of the heat.
Then there's shielding and vacuum. Housing the quantum processors in ultra-high vacuum chambers to get rid of stray atoms that could scatter, and using layers of specialized magnetic shielding, like mu metal, to block out stray electromagnetic fields from the environment. People are even starting to think seriously about shielding against cosmic rays for future large-scale systems.
Oh, cosmic rays too.
Yeah, they can pack a punch. And a huge part of passive mitigation is material science. Constant research into developing ultra-pure, defect-free materials for building the qubits and their surroundings. Because tiny atomic defects or trapped charges within the chip material itself can be significant sources of noise.
So better materials, better isolation. That's the passive approach.
What else? Beyond just isolating, we have active mitigation. This involves using clever control pulses and encodings to actively fight the noise. Dynamical decoupling is a prime example here.
Dynamical decoupling.
Yeah, the idea is to apply carefully timed sequences of control pulses to the qubits. Think of it like a spin echo in magnetic resonance. These pulses effectively reverse the unwanted phase accumulation caused by slowly varying environmental noise. They kind of refocus the qubit's quantum state, canceling out the errors and extending the coherence times, especially T2.
So you're actively manipulating the qubit to undo the environmental effect.
Exactly. It's like sending out an echo signal to cancel out the noise before it builds up too much. Another active approach is using decoherence-free subspaces, or DFS.
Yeah.
Here, the idea is to be really clever about how you encode information. Instead of storing your logical 0 or 1 in a single physical qubit, you encode it into a specific entangled state of multiple physical qubits. You choose an entangled state that is naturally immune to certain types of known symmetric noise.
How does that work?
For example, if the main source of noise affects all qubits in the group in the same way, like a uniform background field, you can encode your information in a state like 0, 1 SM2. Fluctuations in the background field affect both parts of this superposition equally, and the effect cancels out. The encoded information is protected. It's like finding a quiet corner in the larger quantum state space where that specific noise just doesn't have an effect.
It's very clever. Passive isolation, active manipulation. And then there's what many consider the ultimate solution, the holy grail, for building truly large-scale, fault-tolerant quantum computers. Quantum error correction, QEC.
Absolutely. QEC is the cornerstone strategy for the long term. The core principle is, again, redundancy, but it has to be done in a uniquely quantum way. Because of the no-cloning theorem, you can't just copy a quantum state to protect it like you can with classical bits.
Right, no copying allowed.
So instead, QEC encodes the information of one single logical qubit into a complex entangled state spread across multiple physical qubits.
Okay, spreading the information out.
Exactly. And it typically works in 3 stages. First, encoding. You transform the state of your logical qubit, say on Cheryl plus Legerel qub, into this specific, highly entangled state of many physical qubits.
Encode.
Step 2, syndrome measurement. This is the really clever part. You perform collective measurements on groups of the physical qubits, often using extra ancilla qubits. These measurements are designed to tell you if an error occurred, what kind of error it was, like a bit flip or a phase flip, and where it happened on which physical qubit. But, and this is crucial, they do this without collapsing the encoded logical quantum state itself. You learn about the error without destroying the information.
You detect the error without looking at the actual data.
Precisely. You measure the syndrome of the error. And step 3, correction. Based on the syndrome measurement, you know what error occurred and where. So you apply specific quantum gate, a corrective operation, to just that affected physical qubit or qubits to reverse the error and restore the original encoded logical state.
Encode, detect the syndrome. Correct. That sounds powerful.
It is. And there are many different QEC codes. Some foundational examples really illustrate the idea. The simplest is maybe the 3-qubit repetition code. It encodes one logical qubit into 3 physical qubits. For example, 0A becomes 0 error, 1L becomes 111 error. This can detect and correct a single bit flip error on any one of the 3 physical qubits.
Okay, basic but shows the principle.
Exactly. Then a huge landmark was Peter Shor's 9-qubit code. This was the first complete QEC code. It encodes one logical qubit into 9 physical qubits, and it's capable of correcting any arbitrary single qubit error, a bit flip, a phase flip, or any combination of the two. This was a monumental achievement because it proved in principle that fault-tolerant quantum computation was possible.
A theoretical breakthrough.
Absolutely. And moving towards practical implementation, one of the most promising codes today is the surface code. It's a type of topological code where qubits are arranged on a 2D grid, like a checkerboard. It has two major advantages. First, it only requires interactions between nearest neighbor qubits, which is much easier to engineer on a physical chip. Second, it has a relatively high error threshold. That means that as long as the error rate of your physical gates is below a certain percentage, around 1% for the surface code, the QEC process can correct errors faster than they accumulate, allowing you to scale up the computation indefinitely, in principle.
High threshold local interactions. Sounds much more practical.
It's definitely one of the leading candidates for building large-scale machines. So you see this progression, right? From just trying to isolate the system, passive, to actively fighting noise with pulses, dynamical decoupling, to finding immune states, DFS, and finally to actively managing and correcting errors using redundancy, QEC.
Yeah, it really reflects a maturing understanding of decoherence itself. It's a journey from viewing the environment as this insurmountable, monolithic foe to seeing it as a structured, complex challenge that we can actually learn to manage and overcome. What an incredible journey we've taken today, seriously. From that fundamental mystery of quantum reality, why our coffee cups don't exist in superpositions, all the way to the cutting-edge, nitty-gritty practicalities of trying to build a working quantum computer. And decoherence is clearly the central thread connecting it all. This inevitable, natural entanglement with everything else around us. It profoundly explains why our world appears so undeniably classical.
It really does shape our reality, and while it absolutely remains the greatest obstacle, the biggest headache for realizing truly powerful quantum technologies,
The arch nemesis still.
the arch nemesis. But our structured and ever-deepening understanding of its nature, how it works, what kinds of noise dominate in different systems, that understanding has opened the door to increasingly powerful and sophisticated mitigation strategies. From basic shielding all the way up to these incredibly complex quantum error correction codes.
It feels like the quest to master decoherence is clearly far more than just an engineering challenge, though. It's a profound scientific endeavor in itself. It keeps pushing the boundaries of how we understand information, the nature of measurement, and ultimately how our shared, objective classical reality emerges so seamlessly from that bizarre quantum substratum underneath.
Absolutely. And this raises a really important question as we wrap up. As we continue to get better at controlling this delicate quantum dance, as we develop even more sophisticated ways to suppress or even harness decoherence, what new frontiers of knowledge and technology will that actually open up? And how might that, in turn, further reshape our fundamental understanding of the universe itself?